All right, 2015 number 7. This is aluminum is recycled or it's is purified from its original ore. We'll tell you that I've never seen a question on the AP exam where recycling is not the better option. And so at the end of this it says which requires less energy, recycling or extracting it from the ore. I would err on the side of recycling if I was you. Recycling, good. That's generally how that works. So here we go. This is a great little question. A lot of little hiccup kind of tricks in this question. So you gotta be on the ball here. A says calculate the amount of heat needed to purify 1 mole of aluminum originally at 298 Kelvin by melting it. So we're gonna melt it. And the melting point of aluminum is 933. Good. It says the molar heat capacity or specific heat capacity, that's what that is 24 joules per mole times Kelvin. That's a specific heat constant. And then it says the heat of fusion of aluminum is 10.7 kilojoules per mole. This is a tough problem because this is a heating curve problem where you've got a situation where you are taking this aluminum that's solid here and it's starting at 25 Celsius or 25 Celsius or 298 Kelvin, and you've got to heat that aluminum up to get it to 933 Kelvin. So you've got to heat that thing up, and then where it flattens out here, this is the melting point, right? Eventually we would get liquid aluminum here as this heating curve rose again, and then vapor, or then vaporizing, and then vapor, right? And so we have to get to this point. And so we've got to heat it up, and then we've got to melt it. So the reason we have two constants here is this constant is for the specific heat. This is Q equals MCAT. Q equals MC delta T when we're increasing the temperature. And then this flat part here, that's the molar heat of fusion. So that's the delta H of fusion. That's the constant they're giving us, the 10.7. So we've got to do two separate calculations here in part A. And that's why there's 2 points here in part A. And so when we look at this, the way this is going to work is we are going to do the change in temperature part first. And so the energy for the change in temperature part, Q, how much energy we got, is going to equal the mass of the aluminum. It tells us up top we have 1 mole of aluminum. The constant here usually is grams per mole Kelvin. Here it's joules, or sorry, usually it's joules per gram times Kelvin. Here it's joules per mole. Because we only have 1 mole, that's nice. Units matter here, keeping track of our units. So we've got 1 mole of aluminum times that specific heat constant, 24 joules per mole times Kelvin, and then we are multiplying that by the change in temperature. So from 298 Kelvin to 933 Kelvin. The truth is it doesn't matter whether that's Kelvin or Celsius because the change in Kelvin or Celsius are exactly the same. So our change in temperature there is 635 Kelvin, and you can see how the units shake out for us. Kelvins go away, moles go away. We're just left with joules here when we multiply these out. It's roughly, Q is roughly 15,000 joules, which is equal to 15 kilojoules. It takes 15 kilojoules to heat the temperature up. Then we would have here the energy it took to go and melt that solid aluminum. And so the nice part here is we only have 1 mole of aluminum, and they gave us the moles or the kilojoules per 1 mole of heating that up. And so 1 mole is 10.7 kilojoules. And so the flat part of the curve there takes another 10.7 kilojoules of energy. And so we get 1 point for the Q equals MCAT, needing to raise the temperature, and we get 1 point for adding those two together. And so the total amount of energy that it takes to purify that aluminum in part A is those two added together, 25.7 or 26 kilojoules. That's part A. Good. Part B comes back. So you got to do both of them. Just be careful. If you're heating or melting, they've got to give you a conversion factor. If it's a change in temperature and we're looking at heat, it's Q equals MCAT every time. And then we're to part B. Part B says, that's tough, by the way, on part A. It's tough. A lot of people get the Q equals MCAT and don't understand what they're talking about molar heat of fusion, so be careful there. Part B says the equation for the overall process of extracting aluminum from aluminum oxide is shown below, which requires less energy, recycling the aluminum like we did in part A, or extracting the aluminum from aluminum oxide. And it says justify your answer with a calculation. Here's the kicker. When we look at this equation, it tells us the delta H to purify the aluminum. Good, except in this equation, for 1 mole of this reaction, how many moles of aluminum are there? The answer is 2. That's the trick, right? It says justify your answer with a calculation. You should be thinking to yourself, why do I need a calculation here? If that's my delta H, and I have my delta H for the recycling down here, I can just compare those. And so people are like, I don't know where the calculation comes from. The calculation part comes from the fact that that's for 1 mole of this reaction, which gives us 2 moles of aluminum. So the way this really looks is we have 1,675 kilojoules per mole of reaction. I like to set up my units this way. I need to figure out how many moles of aluminum, how many kilojoules per mole aluminum. So the moles of the reaction would go up top. We have 1 mole of reaction per 2 moles of aluminum. That's my calculation. And so when I do that, that gives me 874-ish kilojoules per mole of aluminum produced. And then I'm comparing those values. And I would write a little sentence. Getting 1 mole of aluminum from ore takes more energy than recycling. Make sure you're answering the question, right? And the question is, which requires less energy? So the getting it from the ore takes more energy than recycling. So answer the question. But that's your calculation. That's your answer to the question. There's your 2 points on 7B. Hope that makes sense. If you got questions on it, make sure you yell at me.